All right, guys. Couple examples today. We're going to do one more with the U substitution technique, and then we're getting the absolute value equations. Tomorrow we will work with absolute value inequalities, and then down the road, the next day, following day, we will work with rational equations. So that's kind of where that's plans for this week. When we use U substitution, the technique is not solely for working with factoring. Okay, it is a technique that we can use all across the board in any algebraic situation that we have something that is complex and we want to rewrite it so it's less complex. Okay, then do the algebra with that thing that is less complex. Solve for maybe the U or maybe a different variable, but then at the end, then throw back in the original expression that U took the place of. Does that kind of make sense? So we're going to see this a lot throughout this year, and trying to make certain things a little bit easier for us to manipulate algebraically. You use it in calculus. There's techniques called integration and differentiation. Differentiation is like the first half of calculus, where you're finding slopes of things. It's like the verb for finding slope. And then integration is finding areas, and that's going to be the second half of calculus. Those two techniques have special formulas inside them, and some of those formulas, in order to do that work, requires a use of U substitution. Okay, so I think if we can kind of get the principles learned this year, then when it's introduced to you next year, you don't have to learn the U substitution technique along with differentiation or along with integration at the same time. Okay, so that's kind of what we're going to do here with this example. All right, so this one here, we can look at this, and there's actually two ways of solving this one. Okay, so before any U substitution technique was learned, you had the skills to solve this, but if we were to calculate the time that it takes, it might be inefficient to use that knowledge. But let's go ahead and do this. If I look at this, can I expand that as x squared plus 10x plus 25? Does that make sense? Does this turn into negative 3x minus 15, and then bring down my minus 10 equals 0? Can we do that? Can I then rewrite this as, so we've got the 10x and the negative 3x, it gives me 7x. And this one, just because of the way the numbers worked out, is kind of convenient because those goes away. Positive 25, and that gives me negative 25. So that equals 0. And that introduces an equation that has, it's quadratic, but it doesn't have a c term, right? So when we do that, we can at least bring out an x. There's always a GCF. If we don't have a c term, there's always a GCF of at least x. So I can bring that out, and it leaves me with x plus 7 equals 0. And then you say, well, x is equal to 0. X plus 7 is equal to 0. So there's our two solutions, right? Okay. When we talk about solutions and we start getting multiple solutions, one way that we display our answers usually is that we use these curly braces. And the curly braces identify that we're talking about a set. Okay. So a set is just by definition a collection of things, a collection of objects. They can be names, they could be colors, they could be shapes, symbols, they can be numbers. And these numbers represent our solutions. Okay, so that's kind of the way that we write sets of answers. Okay, we probably haven't used that a whole lot up until this year. But you can, if you have no solutions, you can do the same thing. And we'll talk about that at some point. If you have one solution, you can just put one solution in there, but it's more heavily used when we have multiple solutions. Okay. Part of this course that I'm really interested in is learning or teaching you guys the way of reading math notation. Okay. I think one of the hardest things is for me to throw out a textbook to you or give you a PDF or something, and there be maybe 3, 4, 5 different notations in there of something that you've never seen before, or variables that you've never seen before, and it's usually never explained in the text on what they're doing. They just introduce it and start using it. Does that make sense? And then you've got to kind of, if you want to know what that means, you got to kind of dig on your own to find those things. Okay. I think one of the hardest things about essentially any language is learning the syntax, the order in which we write things, the rules that bind. You know, if I'm talking about Spanish, they've got like upside down question marks and tildes and all that kind of stuff, right? If I don't know what those symbols mean, it's going to be hard for me to really read and interpret the Spanish, right? Okay. Same thing in math. If I don't know what this stuff means, I don't know what these symbols here mean, and the way this is written as notation, there's an issue there, okay, and how I'm going to effectively then move throughout the course. So that's one way of doing that problem. That's probably the way that you would most likely have approached that before yesterday, okay? But would you guys agree that that power there and that power there are in a 1 to 2 relationship? So they're quadratic, right? Okay. Not only are they quadratic here, or quadratic form, they are specifically, if I graph this, it is a quadratic equation. Does that make sense? This will yield a parabola. Yesterday we talked about how that is quadratic in nature, but that's not going to yield a parabola. Okay. This one actually will. So I know that I can factor this, and we can use U substitution, because this thing here and that thing there are the same variable, right? Or variable term. So what I'm going to do is I'm going to let U equal x plus 5. That means then U squared would be x plus 5 squared. Does that make sense to everybody? Okay. So now that gives me U squared minus 3U minus 10 equals 0. At this stage, is that factorable? Yeah. Okay. Now, if it wasn't, and you still use U substitution, let's say that thing was not factorable, you could still use the quadratic formula. But remember what you're solving for here. If I use the quadratic formula with this, my variable is not x anymore, right? It's U. So I would say U equals the opposite of E, plus or minus the square root of B squared minus 4AC over 2A. Okay? You might have to do that in a homework question. But this, bless you, this will factor to what? U minus 5, U plus 2. Okay? So that's going to be U equals 5. That's going to be U equals negative 2, right? So now what do? Back substitute. U was x plus 5. So now I get x to be 0 here, and x to be negative 7 there. Same solution set, right? Now, in this particular question, you might argue, maybe the red one was quicker or the black one was quicker. Right now, I think you'd be, in this question, probably be splitting hairs, okay? But U substitution is going to be a vital component to making things simpler for us, okay? If we think about U squared minus 3U minus 10 and factoring that, that is much simpler than taking x squared plus 10x plus 25 minus 3x minus 15 minus 10 equals 0, condensing that, and then factoring that. Okay. that okay? Even if, if we wrote this as a 4 and that as a 2, if that was the structure of this problem, that's quadratic in form now. You would not want to write x plus 5 times x plus 5 times x plus 5 times x plus 5, right? You wouldn't want to do that distribution, okay? You might use, you guys remember binomial expansion? Did you guys talk about that last year? Pascal's triangle, anything like that? Okay. So you can use that to maybe quicken the x plus 5 to the 4th and get an expression for that. Do the same thing with x plus 5 squared. But once I do that, the fact I'm going to have a 4th degree polynomial, the factoring of that for us right now is impossible. We don't know how to do that. Okay. But if I use U substitution, I can find the solutions to that. Does that make sense? Okay. So it might open the door to making a problem that we initially might think we don't have a technique to solve into a problem that we absolutely can solve. Okay. So in your homework this evening, there's going to be a couple questions that ask you to do that type of substitution. Okay. So we'll talk about absolute value. So what does the absolute value of x mean to us? Okay. So absolute value is the distance an object is from 0. Okay? Distance is always what kind of number? Positive number. Okay, here's my question then. This is my real number line, and 0 is right there. And I travel that blue distance. Okay, so that distance would be C, right? Okay. Can I travel that distance somewhere else? Which way? I can go left. So this distance, this coordinate here would be what? Negative C. And that right there ends up being one of the most important things that we're going to talk about when we talk about absolute value equations and inequalities, is that we can move from 0 a distance of C either to the right or to the left. That's still a distance of C. Okay? But the coordinate to the left is negative C. And that's going to be pivotal for us to understand when we write our rule here in a moment. Okay? Our rule, and I'm going to write this maybe a little bit different than what our textbook does. I'm going to write if the absolute value. Now I'm going to write f of x inside my absolute value. I know we haven't talked about function notation yet, but you did a little bit last year in Algebra 1. I'm just going to write it as f of x, and you're going to see that this is the way calculus does a lot of other things with their rules. Basically what that's standing in for is any function you want, any ax plus b, any ax squared plus bx plus c, any type of algebraic expression that you want to put in there, you can put in there. Does that make sense? I'm going to say that that is equal to c. So absolute value of f of x is equal to c. Okay? Then we will say f of x equals c, or f of x is equal to the opposite of c. Okay? Now when I say or, that's not an optional thing. You have to do both. Okay? It's just saying that your solutions, one of them is to the right of 0, or The other one is to the left of 0. Does that make sense? Okay. When we work with a particular problem, so this is an if-then statement. It's a conditional statement. Remember from geometry we talked about if-then statements? Like if it's raining and the ground is wet, that kind of thing? Okay? And every one of our rules at that juncture in geometry, I told you, every one of your rules that governs mathematics is written as an if-then statement, or can be written as an if-then statement. And that's what we've got here. Okay? And we then went through and said, okay, well, if I'm going to have a rule written as an if-then statement, the only time that I can use this conclusion, the only time that I can apply that stuff right there is if my specific problem matches the hypothesis. Okay? My blue conclusion is only true for true hypotheses, for specific true hypotheses that match that yellow phrase. Does that make sense? And the reason I talk about that is because the number one step that we have to do with working with absolute value equations and inequalities is isolate the absolute value. And the reason we have to isolate the absolute value is because of this rule. Okay? We need to isolate, because that's what's happening here in the yellow, right? Is that the absolute value is all by itself on the left-hand side. Okay? So the only way that I can actually then get rid of the absolute value bars to solve for the variable in this function is to isolate it so I can then do this stuff here in blue. Okay? So we'll come back and talk about that in a little bit more detail and a couple more examples here in a moment. But let's look at this problem here. Does this problem right now, does that yellow, my specific problem, does that match the yellow highlighted up here in my rule? Yes. Okay. So if you remember from geometry, that's called the law of detachment. Okay. If I wrote something like this, I said, if it is raining, then the ground is wet. Okay, so that's my if-then statement. And then I told you a second statement that said, it is raining. Does that match to that? Right? They match. So then the conclusion I can say about it right now in this particular situation is that my ground would be wet, right? Does that make sense, everybody? So, same concept here. Oops. There we go. Same concept. This matches that. Okay, so I've got a true hypothesis here. So now I can make this blue conclusion about the stuff in yellow. So, it says take your function, f of x, which is the 2x minus 5, and you set that equal to c. Well, c is my 3. And then I write or, and take my function f of x, which is 2x minus 5 again, and set that equal to the opposite of 3. And I want to make sure that we understand this. It might seem goofy or silly, but that or doesn't mean I get to choose which one of those I solve. I got to solve them both. Okay, and I will have, I don't want to say I will, but I have had students in the past that they would write both of those, and then they saw the word or, and they attacked it like an either or, right? You do one or the other, and they only did one, and they got half credit. Okay, so make sure we know we got to do both of them. So now let's just solve that. I'm going to go 2x equals 8, and then x is equal to 4, right? Or, we're going to add 5, so we get 2x equals 2, and x equals 1. Okay? And what that does is it effectively puts that expression either to the right-hand side of 0 or to the left-hand side of 0. Does that make sense? Think about plugging 4 in. I plug 4 in, what do you get? You get negative 3 on the left-hand side, don't you? Sorry. You get positive 3. Okay? You get positive 3. So that puts essentially that object on the left, the 2x minus 5. When I plug in 4, it puts it to the right of 0. It puts it 3 units to the right of 0. Okay? If you plug in 1, what do you get? You get -3 inside the absolute value, right? But -3, absolute value, that's still +3, right? So it's true, but that's the situation where now that value of 1 puts you to the left of 0, 3 units. Does that make sense? Okay, so that's what the two solutions mean. One is placing the object to the right of 0, and one is placing it to the left of 0. Okay? Let me copy this. All right, so example 2 here. Does this right here match the yellow in the rule? No. Okay? And that, guys, on this question is the number one error that I get. I get people say, oh, when we deal with absolute value, we drop the bars and we just solve what's left. And we write the word or. We drop the bars, and on the right-hand side of the new equation, we make it negative. So I get that there in yellow without the absolute value bars, and then I get like 3x minus 7 plus 5 equals -14. People solve both those, and they're both wrong, okay? Because right now, this is the idea. If I were to write, yeah. Yeah. Yeah, because when I multiply an equation, when I multiply the right-hand side by a negative, because you're not multiplying the 14 by a negative then. So when I multiply the right-hand side, and I always multiply the right-hand side because there's only going to be one thing that I have to do it to. But you have to distribute the negative through, and you're multiplying to multiple things, right? But you're negating one side, which is fine, so it works. So you can keep doing that approach if you want to. If I were to give you this phrase here, it says, if it is raining, the ground is wet, and then my next statement was the sky is blue, does the phrase the sky is blue match the hypothesis it is raining? No. So can I say anything about the ground now? No. Ground might be wet, might not be wet. I don't know, okay? The law of detachment does not exist here. Those do not match, okay? So, for the same reason, these two things in yellow do not match. So I cannot apply this blue phrase until I make these match. Okay? And that's the rule that I always can come back to. Isolate the absolute value. So when I isolate the absolute value, I'm going to have subtract 5 from both sides, right? And I'll have absolute value of x minus 7 is equal to 3, okay? So now, Anthony, what you're saying is that you take this and you leave it as x minus 7 equals 3, right? And then you also say then the opposite of x minus 7 is equal to 3, right? But think about this. If I multiplied both sides here by that negative, would that turn that into a positive and that a negative? And that then would match my idea that I have the f of x, which is x minus 7, equaling the opposite of 3, and f of x, which is x minus 7, equaling positive 3. So either way, it does it because of what you can do with that negative by multiplying both sides by it. So applying the rule here in yellow, or sorry, not yellow, blue, it's going to be x minus 7 is equal to 3. X minus 7 equals negative 3. Add 7 to both sides. I get 10 and 4, right? Okay. But you can't, like I said, you cannot apply that until you have your specific scenario looks like that thing there. Okay. Like I said, number one error people make, they'll just, and it's weird that they do this, but they're not certain about what's going on here with the absolute value, so they turn them into parentheses. And then they'll write that, and then they'll go like that. Does that kind of make sense what they do? Okay, but that's obviously invalid. You can't do it that way. All right. I want you guys to take a minute and work on example 3 on your own. All right, so what do you do first here? Okay, so you get negative absolute value of 3x plus 6 equals negative 3. Now, okay, so we get absolute value of 3x plus 6 equals 3. So now it'd be 3x plus 6 equals 3, or 3x plus 6 equals negative 3. Does x equal what, negative 1 here? And x equals negative 3 there? Fabulous. Go down to example 5. What are you going to do first there? X minus 5 in absolute value is equal to negative 15. Okay. Does that match? Whoa. Does that match the phrase, if the absolute value of f of x is equal to c, then f of x equals c, or f of x equals negative c? Those match? They do? So that matches that? And here's my argument. Is one of those positive c and one of those negative c? But now somebody might also argue, well, c is just a random variable. I don't know what it is, which I could agree with that. So let's attack it this way. What are these symbols called? Absolute value. What is absolute value? Okay, so when I use a vocabulary word inside discussion, absolute value, I can replace it with the actual definition, right? So instead of saying the absolute value of x minus 5 is equal to negative 15, I could actually say the distance that x minus 5 is from 0 is, for the equal sign, negative 15. And that contradicts what we know about distance, right? Okay. So that is, and that's a common question every year. That is on the final. Okay. It's going to be on our first chapter test, unit test. There's no solution to this. Okay. No solution, because distance can never be negative. Okay. One thing to think about, I've always asked you to graph these things, right? There should always be a graphical approach. You guys know what a graph looks like for absolute value? Okay, it's a V for a certain grouping of functions. Okay, so if I have x minus 5, okay, that's my function. That is linear, right? Okay. What the absolute value does, okay, so this would be like the absolute value of x minus 5 equals y. It takes and makes every single y value, it either keeps it positive or makes it positive. Does that make sense? So there are some y values on this line, okay? Specifically, let's go x minus 5 for values of x less than 5. Does that work? No. I'm not sure what I need to do for the conditional. Basically, I was trying to write this so this highlights this stuff down here. Okay. Can I just type it this way? Nope. All right. It's going to tell me it doesn't know what that means. All right, so I just want to highlight, I can do it in GeoGebra easier, but let's not worry about it. But would you guys agree that everywhere I put my cursor, that those would be negative y values? So when I throw the absolute value around this, do you see how it takes and leaves the y values that were positive, leaves them where they were, but it reflects these negative ones across the y-axis, or sorry, the x-axis? Okay. And one thing to pay attention to is that distance is preserved when we do reflections. That's something we talked about in geometry. This distance right here is 0, -5. That point is going to reflect to 0, +5, right? This point right here, that is 0, -4, or sorry, 1, -4, is going to reflect to 1, +4. Does that make sense, everybody? Okay. Now, that's if the function inside is linear. If the function inside, let's just say I write w is equal to ax squared plus bx plus c. Let's say it's quadratic, and I'm going to, so I call that w. Let's just real quick, and this is kind of like the u substitution. This makes it a little bit simpler. Instead of typing inside my absolute value bars this entire thing, I just type in w. Let's think about why that doesn't change the graph at all. What were all those y values on that red curve? Positive. If I absolute value them, are they still positive, right? Okay. Let's take that curve there. Are there some y values on that curve now that are negative? And if I absolute value them, it gives me that purple curve. That make sense? Okay. So whenever you take the absolute value of a function, and the question is, well, what does it look like? The number one answer is it looks like a V. Well, that's because maybe your experience is only with linear functions. That make sense? But absolute value takes every function, and if there's a portion of it that lies underneath the x-axis, it reflects it above the x-axis. Huh? Oh, no. No. So no solution. So let's think about this graphically. If I'm talking about, well, why did I get no solution here? It's because if I go absolute value of x minus 5, if you're using Desmos and you want to know where the absolute value key is, it's the key right above your enter. You have to hit shift enter, or shift and the key above enter, and it'll put those in. But you can also type in ABS, and it does the same thing. Okay. If I do that, and then I look at the line y equals -15, remember we talked about how the solution to equations is where it's the x value where the left-hand side and the right-hand side cross, right? They don't cross. Okay. So that's the graphical of why we have no solution. Okay. If you are dealing with this last example real quick, something that looks like this. You have two absolute value expressions. Okay. If we are saying that these two things are equal, okay, so let's put 0 right there. If we're saying that the distance this one is away from 0 is the same as the distance this one is away from 0, that means they could both be sitting right there. Does that make sense? Or they both could be sitting right there. Does that make sense? But would you also agree that they're still both the same way or same distance across or away from 0 if the left-hand side was sitting there and the right-hand side was sitting there? Or the right-hand side was sitting there and the left-hand side was sitting there. Does that kind of make sense? Okay. So we have a situation here where we have two absolute values that are equal. They could both be at the same position on the number line, both to the right of 0 or both to the left of 0, or they could be on opposite sides of 0. So that's what allows us to do this next step. Okay. I'm not going to write the rule here. Actually, all right. If absolute value of f of x equals the absolute value of g of x, then f of x equals g of x. Thank you. Or f of x equals the opposite of g of x. This would put them on, both of them on the same side of 0, and that bottom one would put them on opposite sides of 0, but still the same distance from 0. Does that make sense? Okay. So what's that mean? That means I'm going to take this original one, x minus 1 equals 3x plus 2, and I'm going to get rid of the absolute value bars, and I'll solve that. Or, now I'm going to get rid of the absolute value bars again, and then I just negate one of my functions. Left-hand side, I'm going to actually do the left-hand side on this one, because it's a little bit easier. Okay? And it never matters, you don't do both, because if I do both, it gets me back to what this was, right? Just got to negate one of them, and then solve. So then this one is solving, we get 2x equals, what, negative 3? So x equals negative 3 halves. This one here, 2x, oh sorry, 4x, 4. 4x equals negative 1. So x equals negative 1/4. And I know we're going kind of quick here, but I want to make sure we see this graphically. Or not graphically, but with the calculator. If I type in the x minus 1 and type in 3x minus, or 3x plus 2, okay, and we look at those, and I say, okay, well, what if x was equal to, was it negative 3 halves was one solution? Do you see how that puts them, essentially what that would do is it put these two things both on the left-hand side of 0, because this is negative, right? But if I absolute value those two things, is these both positive? So that number would put them both on the same side of 0. If I go negative 1/4, do you see how one is on the left-hand side of 0 and one's on the right-hand side of 0? But still the same distance from 0 of 1.25, right? Okay. Obviously, if you put those in absolute value, you'll see that those two numbers are always positive and the same. Okay. There is an assignment in WebAssign, 15 questions due Thursday. It's about a handful of absolute value equations, handful of U substitution, couple factoring, couple square root stuff from the past.